All right, let us summarize what we've learned from today's lecture. Right? So, a linear second-order differential equation with constant coefficients can be used to model oscillating motions. So then, the coefficients, they have some specific physical meaning, right? So m is the mass, gamma is the damping constant, and k is the spring constant. And so the right-hand side is then called the driving force. Then the spring constant can be also found from this equation. The damping constant cannot be easily found. There will be an exercise for you to figure out how the damping constant can be found from the period of oscillation. Right? Okay. Then, if damping is too large, then the discriminant of the characteristic equation is positive. And so notice that here the bigger the discriminant of the characteristic equation is gamma square minus 4mk, right? So bigger gamma means that the discriminant grows bigger, and of course when gamma is sufficiently large, 2 square root of mk, then the discriminant becomes positive, so which means there is no oscillation. This case is called overdamping. Well, but if the damping constant is not too large, then there are actually oscillations, and they're decreasing in magnitude. So as time goes by, so oscillations become smaller and smaller, but they have follow the certain frequency, in the sense that the frequency is not growing or decreasing as time goes by. So the quasi-frequency remains the same. So they are actually oscillations of the same fixed frequency, but the amplitude is decreasing. And finally, this resonance is a situation when the frequency of the driving force is the same as the natural frequency of the system, right? Or that's for the case of undamped oscillations. Of course, if oscillations are damped, then the resonance happens when the frequency of the driving force is the same as the quasi-frequency. All right, so that's the end of the lecture.